In 1958, the Boeing 707 entered service, one of the very first jetliners. Its cruise speed was about 550 miles per hour. Now, consider the Boeing 787 Dreamliner, a marvel of modern engineering that first flew over half a century later. Its cruise speed is about 560 miles per hour. After decades of incredible progress in computing, materials science, and aerodynamics, commercial aviation has gained a mere 10 miles per hour. We build supersonic fighter jets and rockets that break the bonds of gravity. So why are the passenger planes we fly on every day seemingly stuck in the same speed range as their grandparents from the 1950s? The answer isn't a lack of ambition or technology. It is a story written in the language of invisible forces, catastrophic failures, and a dangerous balancing act performed 7 miles above the Earth. Let's get specific. The paradox isn't just a vague feeling. It's written in the specifications of the aircraft themselves. A first-generation jetliner like the Douglas DC-8, which entered service in 1959, had a typical cruise speed of about 575 miles per hour. That's roughly Mach 0.82, or 82% of the speed of sound at its cruising altitude. Now, let's leap forward over 60 years to the Airbus A350, a triumph of modern aerospace engineering. Its optimal, most efficient cruise speed is around 560 miles per hour, or Mach 0.85. The numbers are virtually interchangeable. Across decades of exponential growth in computing power, materials science, and aerodynamic modeling, the fundamental speed of air travel has remained almost completely static. Your first thought might be the most obvious one: the engines. Surely we just don't have the power to push these massive, multi-hundred-ton machines through the sky any faster. It's a logical guess, but it couldn't be further from the truth. The engines on a modern airliner are technological masterpieces that bear little resemblance to their ancestors. The turbojets on an early Boeing 707 were revolutionary for their time. But a modern high-bypass turbofan engine is in another universe. It's not just a little more powerful, it's an order of magnitude more powerful, and stunningly more fuel-efficient. We have the power. We have had the power for a very long time. So the real puzzle isn't a lack of capability, it's a lack of application. Why build these incredibly powerful and efficient power plants, only to operate them in the same performance envelope as their grandparents from the Eisenhower administration? This reveals that the speed limit isn't a technological barrier we are struggling to overcome. It is an invisible boundary that we have deliberately chosen not to cross. The question is not, why can't we fly faster, but why won't we? To find the answer, we can't look at the gleaming composites and advanced computers of today's jets. The search begins in the past. The first attempts to push the boundaries of commercial flight in the early jet age, to fly higher and faster than ever before, led to a series of mysterious and terrifying disasters. To understand why we fly at the speed we do today, we must first understand the price paid by those who discovered these invisible limits the hard way. The year is 1954. The de Havilland Comet, the world's first commercial jetliner, is the undisputed queen of the skies. It is a vision of the future, flying higher and faster than any passenger plane before it. But then, without warning, 2 comets disintegrate in midair over the Mediterranean Sea. There were no distress calls, no storms, just wreckage falling from a clear blue sky. Investigators faced a terrifying puzzle. To find the answer, they recovered the wreckage from the seabed and painstakingly reassembled the aircraft in a hangar, piece by piece. The cause they discovered was not a bomb or an engine failure. The enemy was invisible, hidden in the very physics of high-altitude flight. To fly fast and efficiently, jets need to fly high, where the thin air creates less drag. But at 35,000 feet, the air is too thin for humans to breathe. So the cabin is pumped full of air, or pressurized, to a comfortable, safe level, like being on a small mountain. This creates an enormous pressure difference. Every square inch of the plane's skin is being pushed on from the inside, with a force trying to burst the fuselage open. In simplified terms, the entire airplane inflates slightly as it climbs to altitude and deflates as it lands. Every single flight. This repeated cycle of stretching and relaxing, known as a pressure cycle, does something insidious to metal. It causes metal fatigue. Over thousands of cycles, microscopic cracks can form and grow, invisible to the naked eye, weakening the structure from within. The comet's designers understood pressurization, but they underestimated the devastating effects of fatigue. And they had made a critical design choice. To give passengers a better view, some of the windows were square. In engineering, sharp corners are a nightmare. Forces that are spread evenly across a smooth surface concentrate intensely at a sharp corner. Investigators concluded that the stress at the corners of the comet's square windows was several times higher than on the rest of the fuselage. These corners acted as a starting point for the invisible fatigue cracks. After a certain number of flights, a crack at a window corner reached a critical length. Then, in an instant, the immense pressure inside the cabin tore the fuselage apart in a catastrophic, explosive decompression. The comet disasters taught a brutal but vital lesson. Engineers learned to build stronger, more fatigue-resistant fuselages. And they made a simple but profound design change: rounded windows. Look at any airliner today. Those oval windows are a direct legacy of the comet. They allow the stress to flow smoothly around the opening, eliminating the dangerous concentration points. They had solved the problem of the plane tearing itself apart, but as they once again tried to push speeds closer to the speed of sound, they encountered another barrier. This one wasn't made of metal, but of air itself. An invisible wall that would fight back with incredible force. Having solved the problem of the aircraft's own structure, engineers now faced a far more abstract and powerful opponent. The limit was no longer in the metal, but in the air itself. As they pushed aircraft designs faster, closer to the speed of sound, they discovered that the air, which had so gracefully lifted them, could turn into a violent and unforgiving barrier. To understand this, we need to look at the elegant curve of an airliner's wing. That shape is what generates lift. In simplified terms, the air flowing over the curved top surface has to travel a longer distance than the air flowing under the flatter bottom surface. To arrive at the back of the wing at the same time, the air on top must accelerate. It must move faster than the plane itself. And here is the critical point. When an airliner is cruising at, say, 85% of the speed of sound, Mach 0.85, the air accelerating over the top of its wing can break the sound barrier. Even though the plane is still subsonic, parts of the airflow around it become supersonic. Where this patch of supersonic air meets the slower air behind it, an invisible phenomenon forms, a shock wave. Some engineers describe this as a near instantaneous, violent change in air pressure and density, a standing wall of compressed air clinging to the surface of the wing. This shock wave does two catastrophic things. First, it creates a massive and abrupt increase in aerodynamic drag, a phenomenon known as drag rise. The smooth, efficient flow of air is shattered. The drag doesn't just increase a little, it spikes upwards exponentially. Trying to push through this barrier requires a colossal amount of engine power, burning fuel at an unsustainable rate for a minuscule gain in speed. It's like a swimmer hitting a wall of invisible molasses. Second, and more dangerously, the shock wave disrupts the airflow over the rest of the wing behind it. The air can separate from the wing's surface, causing a sudden loss of lift. This can trigger a violent, shuddering vibration known as a buffet, shaking the entire aircraft. The shock wave can also interfere with the flight controls on the wing, making the plane difficult to manage. For a conventional airliner, this transonic zone is a region of aerodynamic chaos. That's why planes are designed to cruise just below it, in that sweet spot around Mach 0.85. So there is a wall of drag that makes going faster extremely difficult and inefficient. But this wall is only one side of a very dangerous trap. There is another limit, a minimum speed the plane must maintain to stay in the air. At high altitudes, these two limits, the too fast and the too slow, start to move dangerously close together, creating a narrow sawmick developed to the wing. This is more than minimums that makes finish the planes important and their regional work shorter. There's a symbol well in the plane as getting severe airflow and speed and the close the wing. The second limit that leads not recently move. But these regional limit because of the airflow makes the reveals and regionally necessary. The weather then we find something that find, they will clearly expertise in the similar that help still wait. But this together, creating a narrow corridor of safe flight. What happens if a plane strays outside that corridor? The answer lies in one of modern aviation's most tragic and misunderstood accidents: That invisible wall of drag is the upper limit, the too fast. But at the thin altitudes where jetliners fly, there is also a too slow. To generate enough lift to support its weight in the thin air 7 miles up, a plane must maintain a very high minimum speed. If it flies any slower, the wings can no longer support the aircraft, and it will stall, losing lift and beginning to fall. So, at high altitude, a pilot is flying on a knife's edge. Fly too slow, and you stall. Fly too fast, and you encounter shock waves, drag rise, and potential control issues. As an aircraft climbs higher and higher, these two limits, the minimum stall speed and the maximum critical speed, creep closer and closer together. This creates an ever-narrowing corridor of safe flight, a concept some pilots refer to as the coffin corner. The grave danger of this narrow envelope was tragically illustrated in 2009. Air France Flight 447, an Airbus A330, flying from Rio to Paris, vanished over the Atlantic Ocean. Investigators later concluded that at cruising altitude, high-altitude ice crystals clogged the aircraft's airspeed sensors, known as pitot tubes. This led to unreliable airspeed readings being fed to the flight computers. With no trustworthy data, the autopilot disconnected, handing control back to the pilots. Deprived of the most fundamental piece of information, how fast they were actually flying, and faced with a cascade of alarms, the crew struggled to understand the situation. In the confusion, the aircraft's nose was pitched up too high, its speed decayed, and it entered an aerodynamic stall. Because they had lost a clear sense of their position within the flight envelope, they were unable to recover. This accident highlighted the critical importance of knowing exactly where the aircraft is within that narrow band of safe speeds. In response, modern aviation has built an even stronger defense. Today's airliners, like the Airbus A350 or Boeing 787, are fly-by-wire. The pilot's controls are not directly linked to the control surfaces. Instead, they are inputs to a computer, which then commands the plane to fly. This system includes what's known as flight envelope protection. The software creates a virtual boundary. It will not allow a pilot to make an input that would push the plane too slow into a stall, or too fast into an overspeed condition. The speed limit is now enforced by the plane's own brain. So we now have all the pieces. A structure strong enough for thousands of pressure cycles, an invisible wall of drag that makes high speeds inefficient, and a narrow safety envelope at altitude, now guarded by computers. But this still doesn't fully explain why we don't just build different kinds of planes, like the supersonic Concorde, designed to overcome these limits. The final, and perhaps most important piece of the puzzle, isn't about physics or safety, it's about money. So, we have a structure strong enough to endure the invisible stresses of high-altitude flight. We have a deep understanding of the wall of drag that forms near the speed of sound. And we have advanced computers that act as guardians, keeping the aircraft safely within its narrow flight envelope. This brings us to the final question. Why not simply design a different kind of plane, one built to smash through that sound barrier? The truth is, we already did. Its story reveals the final and most powerful speed limit of all, economics. To fly significantly faster than a modern airliner, you have to pay a steep price in physics and engineering. Each barrier we've discussed must be overcome, and every solution adds immense cost. To handle the extreme forces and temperatures of supersonic flight, you need a much stronger, heavier, and more exotic airframe. To fight against the colossal wall of drag rise, you need engines that are not just more powerful, but burn fuel at a truly ferocious rate. You also need a completely different kind of wing, typically thin, sharp, and heavily swept back. While brilliant at supersonic speeds, this design is often far less efficient at the slower speeds required for takeoff and landing. Each one of these requirements adds weight and complexity, which in turn demands more fuel. And this is not a gentle, linear relationship. The brutal physics of transonic drag mean that a small increase in speed demands a huge penalty in fuel burn. Aviation specialists estimate that trying to push a conventional airliner from Mach 0.85 to Mach 0.95, a speed gain of just 12%, could nearly double the fuel consumed for every mile flown. Suddenly, a plane ticket that was affordable becomes impossibly expensive. This is the economic sweet spot. That cruise speed of around 560 miles per hour, or Mach 0.85, is not a sign of a technological dead end. It is a meticulously calculated point of maximum efficiency. It's the perfect balance that delivers the highest possible speed for the lowest possible fuel cost, making global travel accessible to the masses. The supersonic Concorde was a technological marvel, but it proved this rule by being the exception. It was beautiful and incredibly fast, but it was also so complex and burned so much fuel that a round-trip ticket could cost more than a new car. For an airline, it was an economic catastrophe. So the speed of your flight isn't a sign of stagnant technology. It is the signature of an incredibly optimized system.
That number on the flight tracker represents the calculated intersection of physics, material science, non-negotiable safety, and the financial reality of moving millions of people around the world. It is not the fastest we could go. It is the smartest, safest, and most efficient speed we have learned to fly.